In the early hours of the morning, commuters in a bustling Japanese city were making their way to work, completely unaware that deep beneath them, tectonic plates were shifting. Within seconds, the earth trembled. Buildings swayed, alarms blared, and traffic screeched to a halt. But amid the chaos, one structure stood firm, an elegant, curving bridge stretching over the river. It didn't crack, it didn't collapse, and that moment proved the brilliance behind modern earthquake-proof bridge design. But what makes a bridge resistant to one of nature's most violent forces? Understanding the threat. What earthquakes do to bridges. When an earthquake strikes, the ground doesn't just shake, it shifts horizontally and vertically in waves. A typical structure not built with seismic resilience in mind will snap, twist, or collapse. For a bridge, which spans long distances and often supports heavy loads, the challenge is even greater. The shaking can pull apart bridge supports, twist the deck, the road portion, or collapse entire spans. That's where specialized engineering comes into play. Flexible foundations. Rocking. Instead of breaking. Most earthquake-proof bridges are designed not to resist movement entirely, but to absorb and allow it, just like a tree bends in the wind rather than snapping. Engineers use base isolators, essentially large rubber bearings between the bridge and its supports. These bearings absorb and redirect energy from the ground movement, allowing the bridge to sway safely. Some bridges also include rocking columns that move slightly during a quake and return to their original position. This prevents cracking and reduces stress on the structure. Expansion joints. Breathing room for the bridge. Bridges move a little every day due to temperature changes, but during an earthquake, they can shift much more. Engineers incorporate expansion joints, movable sections between parts of the bridge to accommodate these sudden movements. Without them, the bridge would pull itself apart under stress. Materials that matter. Reinforced resilience. Reinforced concrete, steel cables, and special composite materials are used to construct seismic-resistant bridges. Reinforced concrete includes steel bars that give the structure tensile strength, the ability to stretch without breaking, while new fiber-reinforced polymers are being tested for future builds. Smart technology and sensors. In modern bridges, sensors are embedded to monitor strain, vibrations, and stress in real time. These sensors can detect a problem before it becomes a disaster. After a quake, engineers can review the data to understand how the bridge responded, ensuring safety before reopening it to traffic. Global success stories. Japan's Akashi.